A very good day to doctor. So our group will present about refrigeration. So our group member consists of me, myself, Muhammad Ismail Salihin, Ahmad Iman Zakwan, and also Nur Sajidah. So basically, the experiment's finding will enhance our understanding of how different refrigerants behave within the refrigerant system, and offering valuable insight of selecting appropriate refrigerants for various applications. So this experiment promotes reducing greenhouse gas emissions and encourages the use of sustainable cooling technologies. So I'll pass to the next presenter for the introduction of this experiment.
Okay. Assalamualaikum warahmatullahi wabarakatuh. Okay, my name is Ahmad Imran Zakwan bin Kazilab. My matric number is NA21057. Okay, our group will present about the refrigeration. Okay, first introduction. Okay, the refrigerating unit comprises multiple machine components that utilize to transfer the heat release process compared to natural heat flow. Okay, consist of the four main components like a compressor, evaporation, expansion valve, and condenser. Okay, refrigeration are utilized in air conditioning system and heat pump to transfer heat through the phase change from liquid to gas and the bed. Okay, play a crucial role in providing thermal comfort by enabling functions such as heating, cooling, humidifying, and dehumidifying. Refrigeration has undergone extensive regulation due to concern about their toxicity, environmental impact, and climate change. Okay, next, refrigeration has significantly higher energy transportation capacities compared to water or air. Okay, the expansion valve reduce the pressure and the temperature of the refrigerant convert into a low pressure liquid. Okay, the objective from the refrigeration lab is to determine the coefficient of performance as COP based on the refrigeration system.
Okay, now I will continue with the experimental set of apparatus. So first, we will use the condenser, compressor, filter dryer, expansion valve, cooling tank, hot water tank, water circulating pump, manual valve, drain valve, flow meter from temperature 1 until temperature 6 for the reading, and then high side pressure gauge and also low side pressure gauge. Okay, so now for the procedure, the first step, the refrigerant system and the manual valve are switched on the maximum by turning the handle parallel to the pipe. Second, the system is on for approximately 10 minutes to reach a steady state for condenser fan speed at 1260 RPM. The third one, we set the flow rate to be 50%. And then fourth, the temperatures displayed from T1, T2, T3, T4, and T5 until T6 on the system are recorded for each minute interval. And then the reading for high side and low side pressure gauge also recorded as well. And then for the last step, just repeat the steps 3 and steps 4 by increasing the flow rate of water from 50% water flow rate to the 100% of water flow rate.
Hi, my name is Muhammad Ismail Salihin bin Maksani, MA21053. I will explain about our result and calculation for our refrigerant experiment. In this topic, we will calculate the coefficient of performance, COP, for 50% and 100% water flow rate using data that we get from the experiment. All data and calculation are shown in the slide. Firstly, for 50% water flow rate, we take out average for each reading that we get, like our RPM, our low and high pressure, temperature 1, temperature 2, temperature 3, and temperature 6. Then settle for the data, we then can proceed to the calculation. For point 1, we take the average temperature 6. For point 2, we take the average for temperature 1. And for point 3, we take the average temperature 2. And point 4, we take the average for temperature 3. Then for refrigerant pressure at point 1 and 4, we take the average for low pressure. Then at 2 and 3, we take the high pressure. Then we move for the enthalpy point. At a refrigerant enthalpy point at point 1, 2, and 3, I use pH diagram to get the value for these points. So we can proceed to the refrigerant mass flow rate (MR) using the formula given. Then we calculate our QR, our compressor work, and actual performance number. Then for theoretical compressor work, I refer to the table A12. Then we round out our 0.2 to 690 kilopascal to get our new enthalpy point, which is at enthalpy at saturated vapor H'2. Then we can calculate our theoretical performance number, effective power factor, theoretical compressor output, internal compression output, and compressor drive or coupling power. All this data we can get using the formula that given in the table. Lastly, we can calculate our coefficient of performance COP for this experiment using the formula H1 minus H4 divided by H2 minus H1 times 100%. So for 50% water flow rate, the COP that we get is 57.14%. As we know, for 50% water flow rate, our flow rate is 7 liter per minute. However, in 100%, the flow rate will be 14 liter per minute. Then the data is the same as 50%. We take the average for each reading. Then we proceed to the calculation. As usual, we find the 0.1, 0.2, 0.3, 0.4 at enthalpy point 0.1, 0.2 and 0.3. I forget to explain. For refrigerant enthalpy at 0.1, we look at the pH diagram using the temperature at 0.1 and pressure at 0.1 to get the H1. Then for H2, we use the 0.2 and pressure at PT2 to get our reading for enthalpy 1 and enthalpy 2. Then goes to the below. It's all the same as the 50%. For the theoretical compressor work, we round out our PT2 reading to 730 kPa and using the same table, A12 table, to find our new H'2 value. Then we can proceed to the theoretical performance number, effective power factor. Then for COP, we use the same formula in this experiment also, using H1 minus H4 divided by H2 minus H1 times by 100%. And our COP value for 100% water flow rate is 10.81%. Thank you.
Good day everyone, my name is Nur Sajida binti Hani with matrix number A2024. Today, I will be discussing the key component and varying condition involved in a refrigeration system. Firstly, let's talk about the key component of a basic refrigerator. These include a compressor and evaporator, a condenser and an expansion valve. The compressor creates a relatively low pressure in the evaporator and a relatively high pressure in the condenser. In the condenser, the refrigerant condenses at high pressure and temperature by rejecting energy to the water flowing through the coil. The high pressure liquid then leaves the condenser through an expansion valve. Next, let's discuss some varying conditions involved in a refrigeration system. These include the condenser pressure, evaporator pressure, and water flow rate. These conditions can affect the derived results such as compressor power, compressor suction, and evaporating temperature. Now that we have covered the key components and varying conditions involved in a refrigeration system, let's take a closer look at how some of these components work. The compressor works by compressing the low-pressure refrigerant vapor from evaporator and raising its temperature and pressure. This high-pressure vapor is then sent to the condenser where it condenses into a high-pressure liquid. The role of an expansion valve in a refrigeration system is to reduce the pressure of the high-pressure liquid refrigerant coming from the condenser. This causes some of the liquid to flash into vapor, resulting in a two-phase flow which can be observed through a side glass located along the return line to the evaporator.
Conclusion. In conclusion, the refrigeration system component consists of the compressor, condenser, expansion valve, and evaporator. The assumed how successful in demonstrating the refrigeration system functionality and effectiveness. The coefficient of performance (COP) to measure the refrigeration system and its efficiency was within the expected range. So, the experiment COP valve were aligned with the theoretical value validating the system efficiency. So that's all our group. Thank you.